Hi everyone, and thank you to DTE for organizing this conference and continuing to push it forward. I apologize that the schedule didn't allow me to do this live, but I'm looking forward to continuing the conversations with anyone interested or who has follow-up questions. To introduce myself, I'm Geoffrey Bell. I work at SHoP Architects, where for around 6 years I've been pushing the development of our digital design and delivery workflows, incorporating a lot of different technologies from computational design, scripting, metrology, and interactive visualization tools like virtual and augmented reality. I want to start out with a bit of background on SHoP for anyone not familiar with our office. We're around 200 people. We're located in New York City in the Woolworth Building, which is a beautiful Gothic skyscraper in Lower Manhattan, although we're currently distributed all over the world as we're all working remotely. This is a 3D scan we performed of the lobby of our building. We like to use our own office as a sort of testbed of new technologies or processes, or, as we say, eat our own dog food, and working remotely has been another way of doing that, as a real-time case study of the future of office work. SHoP works on a lot of different project types in a lot of different locations, but something that they all have in common is an exploration of process, rethinking how we make buildings, and an exploration of material, what we make buildings from. We try to use different materials in different ways and let that material inform process and vice versa. Our approach to process comes out of always thinking about how things are put together, not only the end result, but the components that make up a beautiful building and a great spatial experience. So if you look at how something is put together, everything can be broken down into its constituent parts. This seems to us like the natural way to approach buildings. If you ever put together models as a kid, you don't read a set of directions or look through plans and sections, but you know where things go because they fit together with only the most basic instructions. This is something that we've seen for a long time in industrial design, and in the auto industry, and in aerospace. So why can't we think of buildings in the same way? This image is from an old SHoP project called Camera Obscura, where all of the pieces were modeled to fit together and laid out, with the components being sent directly to the machines that make them, and producing no drawings except for very clear diagrams showing how systems work together. And as technology has changed, we've been able to build new tools to improve the way that we can understand and communicate these concepts. Virtual reality, as an example, has an amazing ability to bring a human element into technology, where you can reach out and touch things, pull sections with your hand, pull things apart, put them back together, and understand how a system works in a very clear and very straightforward way. I think of these interactive visualization technologies as a way of de-abstracting design and communication, where for a long time technology has abstracted the way that we designed through a mouse and keyboard and two-dimensional screens. This is opposed to a lot of what you actually see in construction, where at any time where any time you collapse three-dimensional space into two, a lot of clarity is lost, and you create potential for mistakes. So this is why we've been exploring VR and AR as tools for design, for communication, and project delivery. As architects, we work in 3D, so why not leverage that data as much as possible to better understand and communicate schedule, to overlay your digital model onto the construction site, to understand where there are clashes, to better coordinate the installation of the various components. And to be able to track components throughout the building, to select a panel and know that its name, dimensions, quantities, when it's going to be machined and with what machine, packaged and delivered to the site and installed. We use a lot of different tools and processes for this, some of which we've borrowed from the aerospace and automotive industry, like CATIA. And we've also had to invent our own, like the VR and AR apps that you saw before. But also going back to SHoP's earliest projects, like the MoMA PS1 Pavilion. In this case, all the pieces were 3D modeled and printed out at full scale on a plotter to be laid out as templates for assembly. So in this case, the design of the tools became as much a part of the design as the pavilion itself. Jumping forward, the Barclays Center is a great prototype to demonstrate a lot of these ideas, which, if you're not familiar, is a building located in Brooklyn with a corten steel facade that's made up of 11,499 individual panels. All of these are assembled into mega panels, which were all 3D modeled parametrically in CATIA with a part and assembly relationship that allows us to understand the building not only as a complete model, but as assemblies, subassemblies, and components. What that means is we know, for example, that this bracket exists in this mega panel and in any number of other mega panels, or is completely unique. Breaking down the building in this way allows us to track these pieces and assemblies throughout design, delivery, and installation. We produced an app during this process that allows someone in a factory to scan a barcode and let us know where that panel is at any given time. So we can use this knowledge and the geometry that we've produced to create efficiencies in how the panels are being laid out for cutting, nesting unfolded geometry throughout the fabrication process, and send that geometry directly to the individual machines that are doing the cutting and the bending, and create a vast amount of uniqueness across the building while being able to manage the resulting data that comes out of that. And from there, track panels as they're being hung for weathering, being sent out on trucks, and delivered to the site. Still being able to break down the products into their parts and know that they're going to fit together. And as everything's being tracked throughout the process, we know when they arrive, when they're in place, and if there is a problem, it can be responded to in the 3D model before it becomes a much more expensive mistake. But since we're modeling every surface with its thickness, tolerance, and connections, we know ahead of time exactly how they will fit together. And this is a result of looking into the oculus and view of the building from the street. So we learned a lot from Barclays about breaking down buildings into their components and subassemblies, and that's something that has permeated a lot of our work in the years since, going beyond the single building to a portfolio of projects where you can drill down into a building, a specific portion of it, system, structure, MEP, facade, a single mega panel, and even down to a bracket within that assembly. And having the ability to pull information from a specific project and adapt or reuse it in the future. In addition to data surrounding the geometry, like quantities, who worked on it, and how long did it take. So that brings me to another project, the Botswana Innovation Hub, which shares a lot of similarities to Barclays, in this case an anodized aluminum facade, with a similar parametric modeling for fabrication and delivery process. In the case of Botswana, we have around 3,000 facade units. Each of these has 4 to 10 individual panels, where all of the uniqueness of the panels flows out of a very unsophisticated system design, with a few simple inputs of rules like maximum span, cantilever, where do you add in an extra brace? So those are the rules that we build into our parametric models to allow us to design a smaller number of templates. Out of 3,000 units, 6 to 10 individual templates, which can be instantiated into multiple locations along the building, allowing the design inputs to drive the specific dimensions and configurations of the assembly. So each template contains the geometry, the parts and components, the rivet locations of the unit, along with outputs like structural wireframes that allows us to extract the data that we need that after it's been generated parametrically. And using a small number of inputs of design curves and locations, anchor positions to generate everything that the fabricator needs in order to create, assemble, and install the unit. And again, tracking these assemblies is very important because they're being manufactured in South Africa, delivered to Botswana as pieces, and then assembled in the parking garage of the building. And we were able to drastically reduce the number of drawings required by working with the fabricators to send our 3D models directly to the machines, only requiring a few simple assembly drawings and bill of materials. And again, a very simple drawing sent to us to describe the installation sequence, translated very easily to more advanced simulations by leveraging the 3D model and the data that already exists in the geometry. The 3D scanning is also an important part of this process to be able to understand the existing conditions throughout construction, because materials like concrete have very different tolerances to those of our tightly manufactured components. We bring these scans directly into our design environments, create overlays, and we're able to respond to problems much more quickly and cheaply by adjusting our design geometry rather than waiting until the contractor tries to hammer something into place. A few more images of the assembly process. From working in New York, we transmitted the outputs we produced directly to the facade subcontractor in South Africa, who cut and folded the pieces, shipping them to the building for assembly and placement. And looking at the assembled building, each of these unique panels flows into the next to create a really nice undulating facade that also does a great job of shading the interior spaces, making them measurably more comfortable to be in. Another quick project I want to show is a pavilion that we've called Wave Cave. We found at SHoP that pavilions are a really great way to explore process in a very deep way. Wave Cave was an exploration of terracotta and understanding that terracotta is produced in an extrusion process with a very expensive dye. How we can create spatial variation from a single type of extrusion. And one way we found of doing that is changing the way that you cut it. So each extrusion gets cut in 2 directions and assembled to create an undulating form. So with these few simple materials and component types, the variation created through the process, all these components are able to come together to create something new. This process was driven through a Grasshopper script that creates the geometry and at the same time creates the files for the extrusion machine and cutting, along with drawings for quality control and assembly. Through the model, understanding levels of detail and typologies, and the naming of parts to allow for simple tracking and assembly. The generation of the drawings was also set up as part of the design script, so not requiring any additional input on the designer's part to get out the information that the fabricators need. And they all match to the 3D model, which at any point can be brought up for verification and revision. So looking at the pavilion as installed in Milan. In all of this, I think the importance of prototyping and making can't be overstated. To that end, we have a space in Bushwick with a woodshop, CNC machines, welding, 3D printing, and an industrial robot arm. We use this space for full-scale mock-ups, prototyping, and experimentation to better understand tools and processes and what goes into actually constructing what we design, so that when we talk to fabricators and contractors, we're starting from a place of knowledge. This also allows us to do things like explore the relationship between automated process and handcraft. Recently at Acadia, we led a workshop that explored the relationship between technology and making through VR, AR, and robotics. So this started with a custom VR design environment that we created with relatively simple interfaces to allow users to drag these simple wood pieces very naturally, and the toolpaths for cutting and assembly are automatically created. The model then goes to the KUKA using augmented reality to understand timing and placement, along with the assembly process, eliminating drawings by scanning a part and seeing it highlighted in space so you know exactly where it needs to go. We also internally run a series of courses that we call SHoP University, where we explore processes like welding, casting, parametric design, VR and AR, along with anything else from game design to cocktail making or skateboard design. And all of this we found is a great way of sharing knowledge within the office in a much more fluid and approachable way than being tied to a specific project. And just before we all moved out for remote work, we opened a new floor in our office with some additional desk space to allow us to spread out, but also opening up more opportunities for individual designers to do their own making and experimenting with materials and tools. Along with a new technology hub that incorporates a cylindrical immersive screen, VR, AR, and 3D scanning. This and the makerspace are adjacent to each other, which creates a lot of opportunity for seamless workflows between physical modeling and digital design, where you can cut a mass out of foam, 3D scan it, and very quickly explore it at full scale, perform solar and wind studies, or overlay with existing digital models. So out of all of the direct model to fabrication work, I think a very clear translation of our work on facades is offsite manufacturing for full buildings. This includes research into timber, CLT, and also volumetric modular construction, which hasn't really been explored much from a high-rise perspective, but makes a lot of sense in a place like New York City, where on-site labor costs are high, and the cost of leaving a crane up and staging adds a lot to the total cost of a project. So I won't reiterate again the whole part about parts and assemblies, but to say here again, a modular approach is all about breaking down the building down into its constituent components, and having all of this in a digital twin allows us to use this 3D data and metadata to inform design, delivery, logistics, and output the data drawings and models that each stakeholder needs in real time. And also adding in a generative process to quickly understand a site and what we can build on it, extract metrics and early costs and quantity takeoffs at both the building and unit level, adjust layouts, and see things update in real time. And automating the process of moving between softwares to allow us to create high-resolution fabrication models on very lightweight design geometry. And once we have all this information that has been generated, leveraging it to understand process in the factory and on site, setting up sequences along with material and labor requirements at each step, and simulating the process and the equipment used in the factory to better understand timing and space requirements and the impact that our design has on these very concrete manufacturing needs. So finally, where is all this going? I've shown some examples at the fabrication level, but we're finding more and more the value of this process at a master plan scale, where we can use rule sets and knowledge from past work and quickly apply it to a building to understand the implications of cost, time, and material at a granular level from the beginning of the project, and apply it across a large site or even at city scale, generating new geometry from existing rule sets, using the rules embedded in our design templates, and linking it to external data from the site to allow the buildings to respond in real time. This is a prototype developed at Dassault's Design in the Age of Experience hackathon, in which we took city data from their urban platform and pulled that into individual blocks to bring in data like style, scale, setback, materials used, and variation in building stock to create a number of different typologies throughout the city, moving from old to new, moving from traditional to contemporary. So extracting data from a city scale, applying it to a block scale, and very quickly generating a number of different possibilities. We can take a site, break it down into modular building components, and very quickly understand the logistic and material requirements. Drill down into a building, its components and subcomponents within, so that even at the large-scale approach of a master plan, we can start thinking on a detail level from the very beginning of a project. And through this, fluidly moving back and forth between scales to better understand what we're doing in terms of the architecture itself and everything that comes along with it. So thank you very much for your time, and I look forward to connecting with everyone in the future.